the dimensions of space-time. When one tries to specify a point in space-time, one describes where the point is by providing 3 coordinates. Then one should define when by providing a time frame. But there is a third parameter which answers the question what is at that point. And that fifth parameter, which should be considered, is an instantaneous electromagnetic field intensity. So the instantaneous electromagnetic field intensity is a critical fifth dimension of space-time. Consider the following facts. Firstly, we have Coulomb's law, and Coulomb's law tells us that around every charge, a field will form. And another charge moving through that field will be either attracted or repelled to the originating charge. The second fact to be considered is that a charge and its field, which could be quite large, is not a super rigid, instantly at a distance object. What happens is the charge arrives at a point, and then the field forms slightly after that, with moving out radially from the origin at the speed of light. So it forms at the speed of light around the charge. That's the second point. The third point is that subatomic particles move extremely fast. Electrons move much faster than the atoms in which they are a part of. And then quarks move faster again, going close to the speed of light. So there you have an object moving near the speed of light and fields forming at the speed of light. If you accept these 3 points, you must come to the inescapable conclusion that fields, the instantaneous fields around quarks, must pulsate each time the quark passes. So each time it cycles within a proton or a neutron, there must be a pulse of high intensity. Why is this fifth dimension so difficult to detect, or why is it difficult to detect? A, the pulses occur at incredibly high frequency. You have something moving near the speed of light in the tiny space of a proton or a neutron. So as it cycles, you will have a very high frequency, even higher than gamma radiation. So this will be some of the highest frequencies possible. The second reason why they're hard to measure is that when we have a charge and a high intensity pulse passes it, it's first pushing the charge one way, passing the charge, then pushing the charge the other way, as the charge, either if it's the same sign as the passing wave, it will seek to move away from the higher intensity, or if it's the opposite sign, it'll seek to move towards the higher intensity. So it's one way then the other with little net effect, and even very little net effect on overall solids, atoms, and so on. So that's the second reason. And the third reason, C, these fields, you have roughly equal strength positive high intensity pulses and negative high intensity pulses. So over time, you will have a net neutral coming out of most atoms. You'll have a net neutral field. So the field intensity is netting out at zero over slightly long periods of time where you just need a few cycles, despite the immediate thing being either extremely high or extremely low. It's sort of like alternating current or something, where it's extreme peaks, though, but with extreme peaks. So for those three reasons, they're very hard to detect. However, before you discount this theory as being impossible to verify, consider that there are some well-known facts, well-known phenomena which are consistent with these type of fields. The first one is if we look at electrons. When scientists first looked at electrons, they were expecting smooth motion around the nucleus. But instead, they found very erratic motion around the nucleus, where you couldn't even say exactly where it was going to be. You could only come up with a region where it was most likely to be. You could only come up with a probability distribution. It's almost as if the electron was in the throes of some giant waves or something. So this is quite consistent with high intensity, extreme high intensity electromagnetic pulses. Then the second phenomenon, which is consistent with this theory, is that, let's look at quarks. Quarks being a quark moving near the speed of light as a high intensity electromagnetic field pulse comes up behind it. And they're both moving near the speed of light. So this is the longest type of interaction that will occur between charges and these pulses. It's where you have a same sign field pulse and a same sign quark. So what happens is the quark moving forward at the speed of light is pushed forward because they repel at the speed of light, pushed towards the speed of light, and they're sort of they move together. So while they're moving together, the field generated by the quark is added to the field of the peak. So the peak grows a little stronger. And at the same time, the quark is unable to accelerate normally. Usually when these peaks hit a charge, it will push it pretty hard one way. Like the electron is thrown forward. But the quark, or thrown backward, either way. But the quark can't do that because it's already moving near the speed of light, so it has a diminished push forward. Then, of course, the high intensity pulse passes the quark, and it'll push it back. The push back will be of normal strength because it's slowing it down, and it wants to slow down. Moving near the speed of light, slowing down, there's no resistance to slowing down. So the net effect of a super high intensity pulse on a quark of the same sign, which we would take to build these waves, is a slight pushback. And that slight pushback, that's your gravity. So it's absolutely consistent with high intensity, high frequency electromagnetic pulses. Is this too far-fetched to be believed? Well, if we eliminate the impossible being smooth fields around protons and neutrons. Impossible, since the field forms at the speed of light and the quarks are moving at the speed of light. So if we eliminate the impossible, we are left with the possible, however improbable. Very high intensity pulses moving at the speed of light. How strong? So strong that once they reach the surface of a large body, they're so strong that they are able to cross great distances of space and still have strength when they get, for example, from the sun to the edge of the solar system, still having strength after all that distance to hold the planets in the solar system. So if we eliminate the impossible, we're left with the possible, however improbable. That's the way I see it. Thank you.